Hi, Mr. Simone again from Hammond Middle School. The purpose of this video is to solve systems graphically, but more importantly, instead of looking at systems that have one solution, we're looking at systems that have either infinite or no solutions. And we're going to talk about some of the differences with those. For this one, I'm actually going to start with this problem over here, all right, where we have y equals 2/3 x minus 3, and then y equals 4/6 x plus 2. I'm going to skip over that first one because we've already talked about those types of problems. So for this one, I often tell my students to identify two pieces of information, which includes the slope, in this case is 2/3, and our b, which is the y-intercept, is going to be -3. I know it says -3, but we can consider that -3. The slope tells us the direction we're headed, so it's going to be up 2 and to the right 3. And we're going to be starting at that value of -3. Now you'll notice that my graph isn't labeled. If you need to write in the labels, that's fine, but we'll practice without it. So -3, that's going to be my y-intercept, and then I'll use the pattern of 2/3 to write in the rest of my points. So up 2 to the right 3 spaces, up 2 to the right 3 spaces. You'll notice it doesn't go off that way. And then we're going to do the opposite direction, so we're going to go down 2 to the left 3, down 2 to the left 3, 1, 2, 3, and those are our points for that equation. If you watched earlier videos, you know that we connect our points, draw arrows through them, and then also label it. So this is y equals 2/3 x minus 3. All right. From here, we will continue by graphing the second line. So this one, we have a slope of 4/6, and our y-intercept, which is b, is +2. Start with the same kind of process. We're going to plot that +2 as my y-intercept, and then my slope says to go up 4 and over 6 spaces. So I'm going to go up 1, 2, 3, 4, and over 6. 1, 2, 3, 4, 5, 6. Okay? Obviously, I can't go any further to the right, so we can go in the opposite direction. We'll go down 4, 1, 2, 3, 4, and to the left 6. 1, 2, 3, 4, 5, 6. And we'll connect them together. And we'll label it. So this is y equals 4/6x plus 2. Now this does happen sometimes where you go to graph systems and they don't necessarily connect. These ones will never connect because they are parallel. One of the ways that we can tell is by looking at the slope. This slope of this equation can be simplified from 4/6 to 2/3. So having the same exact slope but different y-intercepts will result in something that's known as no solution. So this one we can just write has no solution. And that's what you write. Parallel lines, they have the same slope, different y-intercepts, they will never intersect. So there is no one solution answer. Sometimes though, there will be instances where the graph may have two lines that are not necessarily parallel, but we don't actually see where they intersect. If that happens, you either have to change the scale of your graph, or it might work to solve your system using one of the other methods, either elimination or substitution. But for now, if this happens, this is a special case. They both have the exact same slope, different y-intercepts, so this is a no solution, parallel lines. All right, and then the other one I want to go over is going to be this one, number 7. All right, so number 7, we'll start with the first one. The y equals 1/2 x plus 1. So my slope is 1/2, and my y-intercept is just 1. So we'll graph that. Starting off at y equals 1. And we'll follow that slope. So up 1 over 2, up 1 over 2, up 1 over 2, and so on and so forth. go in the reverse direction, you can do that. You can go down 1 to the left 2, down 1 to the left 2, down 1 to the left 2, and I usually tell my students to kind of fill out the graph if they can. It makes for good practice. Connect our points together, arrows on the end, and we can label it. So I'll put it over here. So this is y equals 1/2 x plus 1. Now some of you, when you're watching the video, may notice like, hey, there's something interesting here. I noticed that the second one has the same exact slope. It's written as 3/6, but 3/6 is equivalent to that 1/2. So we know they have the same slope. And some of my students right off the bat will be like, oh, they're parallel. So there's no solution. But you'll also notice that the y-intercept, you might have seen that as well, the y-intercept is exactly the same. If this happens where you have two equations, two linear equations that are exactly the same, all right, if you try to graph that second line, you're going to notice that that second line is actually on the original line. If that happens, this is not known as a no solution, it's not known as a one solution, but this is known as an infinite solution. And I usually tell my students that they can use the infinity sign and just write solution. And when this happens, it means that no matter what x value you choose, you'll have the same exact y answer for both equations because they are exactly the same, even though they're slightly written differently. I do have some students that prefer to try to graph them on themselves. So you have that positive 1, you go up 3 over 6, or you can go down 3 and to the left 6, and you'll notice that they are in fact on the same graph. All right, so I know in previous videos we talked about one solution problems where obviously you graph it and they do intersect. In the event that you have linear equations and they have the same slope but different y-intercepts, they're going to be parallel, so no solution. If the lines are exactly the same, obviously it's going to be an infinite solution. Just be careful, be mindful that there are certain scenarios where you might have two lines that look like they're going to intersect, but given the scale that you have, they don't. That's not a no solution. That is, obviously going to be a one solution. Just make sure that you either change the scale or solve it in a different way. I hope this video helped. It was a quick one. So again, no solution and infinite solution for systems of equations, solving graphically. Keep working.